Lesson 96. To begin, I would like you to take some time to think about this. You are using a scale that measures to the nearest 0.1 grams to weigh an apple. The reading shows 132.7 grams. Select the statement that best represents this observation. A. The apple weighs exactly 132.7 grams. B. The apple weighs less than 132.7 grams. C. The apple weighs more than 132.7 grams. And D. The weight lies somewhere between 132.65 grams and 132.75 grams. Most of you study science, and I hope your answer was D, right? Because probably in the first or second lessons in your science classes, your teacher would talk about measurements and tell you that, well, you can never be certain about a measurement, no matter how accurate your device is. So that's why you have to factor in uncertainties when you do your labs. Similarly, when we think of a continuous variable x, we can only talk about the probability that a measured value lies in an interval, okay? And we know that the probability of one event being exactly equal to a number, so x equals to only one number, little x, is 0. That is, i.e., if I'm thinking about the probability of a less than or equal to x, less than or equal to another number b, it is the same as saying the probability of a less than x, less than or equal to b, or p of a less than x, less than b, or p of a less than x, less than or equal to b. They are all equivalent. Now let's continue to look at continuous random variables. So a continuous random variable forms a probability density function. We call this PDF. For function f to be the probability density function of a continuous random variable x, so we say PDF of x, it must verify the following axioms. So first of all, this function must always be positive. It should be greater than or equal to 0, or its graph should always rest above the x-axis, okay? And then this allows us to find the area under the curve which represents the probability. So this takes us to the second axiom, which is the integral of f of x dx, so the area, from negative infinity to positive infinity must always equal to 1. Because of course, if I'm talking about a probability distribution, the sum of all the probabilities is always equal to 1. So in the box, the area under the curve between the interval x1 and x2 represents the probability of p of x1 less than or equal to the continuous random variable x is less than or equal to x2 can be calculated by taking the definite integral of f of x dx from x1 to x2. Okay? Let's take a look at example 1. So here we have f of x defined in a piecewise function that f of x is equal to k from 0 to pi over 2, k sine x from pi over 2 to pi, and 0 elsewhere. Part A, we need to look for the value of the constant k. Knowing the first axiom and the second axiom, we have to make sure two things. K is always above the x-axis, and also I know that the total area below the curve of f of x must equal to 1. So we can calculate the area by splitting into the two regions. First of all, from 0 to pi over 2, k dx, And then the second region from pi over 2 to pi, which takes on k sine x dx. The rest is 0, so I'm not going to add that term, but this sum must equal to 1. Okay, so let's integrate. Here I have kx from pi over 2, 0. Well, from 0 to pi over 2, I should say, plus the integral of k sine x, which is negative k cos x, from pi over 2 to pi. This must equal to 1. So let's substitute those endpoints. Here I have k times pi over 2 minus 0 plus negative k cos pi minus negative k cos pi over 2. So let's move to the side to continue. I have k pi over 2. Cos pi is negative 1, so plus k. Cos pi over 2 is 0, so that's equal to 1. I can factor out k here. So k is pi over 2 plus 2 over 2. So pi plus 2 over 2. So that's k is equal to 2 over pi plus 2. Okay. If you work this out, this is approximately 0.389 rounded to 3 significant figures. Okay. Sketch a graph of the function. So let's do that. So from 0 to pi over 2, so let's say this is pi over 2, we have k. So k now is 0.389. Okay. And then after that, up to pi, we have the function k sine x. So sine pi over 2 is 1 times k. So we start here. And then sine pi is 0. So we have this region here. The rest of it are 0. So let's include that, okay, to complete our sketch. And this is x. So let me label the x's as well. Part C. Find p of x less than 1. So I know that the value of pi over 2 is like 3.14 divided by 2, so that's slightly higher than 1. That means that in this part, 1 would be somewhere here, let's assume, and we're looking for this area, okay? So knowing the relationship between probability of continuous random variables and area or integrals, this can be found by going from 0 to 1 of the function k. But now we know that this is 2 over pi plus 2 dx. Okay, so this is going to work out to 2 over pi plus 2 being a constant times x from 0 to 1, which is just 2 over pi plus 2. Okay. If I take out a calculator, p of x less than 1 is approximately 0.389, or you use that number that you have calculated in part A. Now, part B, we have to find the probability of x between 1 and pi. So let's go back to the graph or the function. From 1, which is this point here, to pi, we are actually transitioning from one function to another, right? So first of all, I'm at the constant function, and then in the second part, I have this region that I have to look for. So in our calculation, we need to actually separate the integral into two sections using two functions definitions. So here we go. We have from 1 up to pi over 2, we are using 2 over pi plus 2 dx. Plus, in the second part, between pi over 2 to pi, I'm using 2 over pi plus 2 sine x dx. Okay? Does that make sense? So, The next part is just to take the integrals. But what will help us is to perhaps factor out 2 over pi plus 2, okay, to simplify our work. And then we can say the first integral becomes x from 1 to pi over 2, okay? The next integral will become negative cosine x pi over 2, like that, okay? So here we have 2 over pi plus 2. The first bit, we have pi over 2 minus 1 plus negative cosine pi, I'll just do it in the ugly way, minus negative, so plus cosine pi over 2. Okay, maybe I'll do that. Okie doke. So let me move to the side here. Seems like we're being cut off at the bottom. So here I have 2 over pi plus 2 times pi over 2 minus 1. Negative cos pi is minus 1. So plus 1. And cos, that's 0. So that's nice. This is just pi over 2 in brackets. And the 2 and the 2 can reduce. So I have pi over pi plus 2 to be exact. And if you prefer to round it, this works out to 0.611. Round it to 3 significant figures. Okay? Next, let's talk about measurements of center and spread for PDFs. For continuous random variable x with probability density function f of x on the interval from x1 to x2, you just think of what you already know statistically. Okay. The mode is the value of x that gives you the highest point on the function. Basically, it maximizes f of x, because you can think of the profile of a very random PDF that looks weird like that. Where would the mode be? Of course, the mode would be the highest point, so this would be the mode. Okay, so you register that x value as the mode. How about the median? Well, the median marks the midpoint of your entire data set, right? Half of, the x values fall below this particular median x value, and half of your other probability fall higher to the right of that. So that means that if I consider finding, the probability of 0.5, then I can go from either negative infinity to the median, m, or I can start from the median and go all the way to the upper half of your data set or your distribution, which is, which makes this integral equal to 0.5. The mean of a probability distribution, we call it the expected value, right, in the study of discrete random variable. When we are dealing with continuous random variable, it's very similar, because look at the format here. I have x times the probability of each value of x, but we need to sum them all up, right? Remember, back then for discrete, our v, we call e of x the sum of x p of x, right? So this is really the same thing when you multiply x by the integral, okay? Now variance is very similar again. It's really the sum, so think of that integral symbol as the sum of the deviation square, x minus mu squared, times f of x dx, okay? And then standard deviation is still the sigma, which is the square root of the variance. So nothing has changed at all. Here is example 2. A continuous random variable x has PDF given by the function f of x from 0 to 2. Find the value of k. All right. So here we do recognize that this is somewhat of a cubic function, right? K is a constant. We can start from the most basic definition or axiom, which is the entire function, when it's not zero, if I take the integral of that, must equal to 1. That's the total probability. So here, if I factor out the k, I am dealing with x times, let's expand this, 4 minus 4x plus x squared dx equals to 1, which means that I will have 4x integral, which is 4x squared over 2, 2x squared, minus 4x squared integral, 4x cubed over 3, plus x cubed interval, x to the 4 over 4, from 0 to 2. And this whole thing is equal to 1. Okay, moving on. I have then k of 2 squared 4, 8, minus 8 times 4, 32 over 3, and then 16 over 4, 4. And then 0 is everything, so minus 0. Okay, so that's equal to 1. Simplifying that, I have 12, 36 over 3, 4 over 3, so k is 3 over 4. Okay. Why don't we sketch the profile of this function? Let's take a look at what it looks like. So let me set up the axes. And then, let's see. So 0 is 0. And then 2 minus x squared, so 2 for sure. And then k is positive, so that means I will have something like this. Okay, it may not be the most accurate sketch, but that will do the job. So the maximum will be somewhere here. Okay. So part B, find a mode, median, mean, and standard deviation. So let's start with the mode. I need to find the max of f of x. So what will be a convenient thing to do to find a maximum of a function? Of course, first derivative. So f of x, let's write this out. This is 3 over 4 times 4x minus 4x squared plus x cubed. I'm using like the second line in the last part here, which is 3x minus 3x squared plus 3 over 4 x cubed. This is f of x. So now I need f prime of x, which is 3 minus 6x plus 9 over 4 x squared. Correct? So make this equal to 0. Let's see. Can I simplify this somewhat? I can do, what can I do? If I divide by 3 over 4, what will happen? If I divide by 3 over 4, so multiply by 4 over 3, I have 4. 4 over 3 times 6, 8x, plus 3x squared. Okay? And then, can I factor this? I think so. I have 3x squared, so 3x times x, right? I need 8, so that must be a 2 to make 6, a 2, and then both negative, okay? So x is either 2 over 3 or x is equal to 2. But then we know that x equals to 2 gives us a 0. So that cannot be the mode. Therefore, the mode must be 2 over 3. Okay, so we can cross that out. Okay, so that's the first calculation. Then we want to know what the median is. So let's do that. Okay, so the median can be found by going from negative infinity up to the median point. But from this function, I know that anything to the left of 0 is 0. So theoretically, I can start from 0, which is more convenient, up to m of the function 3x minus 3x squared plus 3 over 4 x cubed dx. This must equal to 0.5, right? Half, the bottom half. So let's integrate. I have 3x squared over 2 minus x cubed over 3 times 3, so just x cubed u. So just x cubed plus x to the 4 over 4, so 3x to the 4 over 16. Okay, and then this is from 0 to m. And this is equal to 0.5. Let's keep going. I have 3m squared over 2 minus m cubed plus 3m to the power of 4 over 16 equal to 0.5. Now this is a quartic. So using a calculator, we can use the solver on there, or you can do it graphically, whichever way you prefer. M works out to approximately 0.771, rounded to 3 significant figures. Okay, so this is the median. What's next? Okay, next we have the mean. And by definition, the mean can be found by using the function x f of x dx. Okay, and we do it from negative infinity to infinity. But of course, for our function, we only need to find it from 0 to 2 when the function is non-zero. Okay, so we already know what f of x is in expanded form. So I need to find this integral by multiplying x into f of x first. So 3x squared minus 3x cubed plus 3 over 4 x to the power 4 dx. Okay, so 1 degree higher for each term. So x cubed over 3 times 3, x cubed, minus 3x to the 4 over 4, plus x5 over 5. So 3x5 over 5 times 4, 20. From 0 to 2, 8 minus 16 over 4, 4, 12, plus 32 divided by 20 times 3, 24 over 5, which works out to approximately, is it exact? Yes, exactly 0.8, I believe. Okay, you can also write this as e of x or as mu. It's up to you. Okay, and then we have also got standard deviation, which is the square root of the variance. Okay, so this is the square root of var of x. Okay, so let's start by finding var of x. And the formula for finding the variance, you can see it in the card above. I'm going to rely on my formula booklet here. This is equal to, from x1 to x2, x squared times f of x dx minus blah, blah, blah. Okay, so 0 to 2 then, that's our boundary. X squared times f of x dx minus mu squared. Okay, so here we have the integral from 0 to 2, x squared, so times f of x, 3x cubed, minus 3x squared times x squared, x4, plus 3 over 4 x cubed times x squared x5 dx minus mu squared. Mu we found to be 0.8. Okay, so what do we have? 3x4 over 4 minus 3x5 over 5 plus 3x6 over 6, which is x6 over 4 times 2, 8. From 0 to 2 minus 0.8 squared. This gives me sigma equaling to 0.0457, and if I square root that to calculate the standard deviation, I get 0.214. Round it to 3 sig figs.